Alright, sorry about that. We're keeping my older son's dog. He's kind of a handful. Okay, so with this scenario, if this value is the same, okay, we're going to have different combinations of mass and acceleration for our bowling ball and our golf ball. So our bowling ball is going to have a large mass and a smaller acceleration. And then our golf ball has a smaller mass and a larger acceleration. Okay, so the golf ball is going to have the larger acceleration. Because it has a smaller mass. And if you think about it, I tried to do this a while back in class. I had a golf ball and a bowling ball, and I tried to push them with roughly the same amount of force. The bowling ball doesn't roll as much across the room when you do that as the golf ball does, because the golf ball is accelerating more. It has more it has less mass and less inertia. Remember, inertia is our tendency to resist motion than my bowling ball does. So, okay, so last questions have to do with circular motion, which we just talked about, and then gravitation, which we're actually talking about today. So here is an object going in a circular path. We want to describe the direction of these vectors. So my centripetal force, that's my force keeping it in the circle, is towards the center of the circle. My centripetal acceleration is also towards the center. It's the same direction as the force. And my velocity is tangent to the circle. Remember, we said tangent means touching. And it's also changing directions. As it goes around the circle. So the velocity is going to change, like it's pointing. Imagine me drawing this vector as it goes around the outside of the circle, and then always pointing into the center of the circle is going to be force and acceleration, and they're perpendicular to each other. Okay, so we got an object with a mass, a given velocity, and a given radius. What's the centripetal acceleration? This is an equation we looked at Friday. We do v squared divided by r. So I've got my velocity is 4 meters per second. I got to square that, divide that by 1.3, and that's going to give me, let's see, got to get my handy dandy calculator out again. 4 squared is 16, divided by 1.3 gives me 12.3 meters per second per second. Remember, this is acceleration. It's like the other accelerations we've looked at. It's just for an object moving in a circular motion. And then if I want the force, I'm just going to do my Newton's second law here. Again, mass times acceleration. This is my acceleration. The mass was 3.2, so 3.2 times 12.3 gives me 39.4, and that's newtons. That's still a force, still in newtons. Okay, then we've got gravitation. We've got this equation. We're actually going to go through this today. So what relationship exists between mass and force? This is a direct relationship. If mass goes up for one or both objects here, and these are for like a planet and a sun, or a planet and a moon, okay, big objects. What would a direct graph look like? It looks like this. Okay, so it's like a linear relationship. As mass gets bigger, force also gets bigger. What relationship exists between distance and force? This is an inverse square because of the equation here. Distance is on the bottom, so inverse, and it's squared. And this graph looks like this, where I've got force, distance. I've got this curve that drops off really steeply. Okay, so as distance gets bigger, force is going to get smaller, and it gets smaller by the square. So it gets smaller really fast. And that's just the math part of that equation. How would force of gravity change if the mass of one doubled and the mass of the other tripled? So this is our rule, what we call rule of ones, where we pretend everything in this equation here is equal to 1. We don't have to worry about this g because it's a constant. And then we change whatever factors changed and see what happens to our force of gravity. So I have force of gravity is 1 times 1 divided by 1 squared for my mass 1, mass 2, and my distance squared. And then I'm going to change the masses. I'm going to have 3 times 2 divided by 1 squared. Distance is not changing. Mass of one object doubled, that's my 2. Mass of the other tripled, that's my 3. So my force of gravity is now going to be 6 times greater than it was. And this is where I'm doing a factor of change. I'm not necessarily getting numbers. I am getting a factor by which my force of gravity changed. Okay. How would it change if the distance was cut in half? So now I'm going to have force of gravity. It's 1 times 1 divided by 1/2, and I got to square that, because the distance is going to be cut in half. So now I've got 1 divided by 1/4, and I have to do the keep, change, flip, or whatever. This fraction is going to flip up, basically. And I'm going to end up with 4 times. When I bring my objects closer together, my force is going to be greater. Last one, distance is now going to be tripled. So now I've got force of gravity is 1 times 1 for the mass divided by 3 squared for the distance being tripled, and that gives me 1/9. So now if I triple my distance, if I make them 3 times farther apart, that's going to drop my force of gravity value. Okay, so that is the study guide.